All right, hello again, everyone, and welcome to the second video recording that you are required to watch this weekend. Today we'll be talking about, or in this video, we'll be talking about Zorn's lemma, one important technical result not only in set theory, but also in other branches of mathematics, all right? So in the last video, we talked about the well-ordering principle. So ngayon naman, itong Zorn's lemma, which actually is equivalent to the axiom of choice, which you have seen as one of the Zermelo-Fraenkel axioms for set theory, and the well-ordering principle, which we just discussed earlier. All right. So medyo may joke dito ako nakita about the Zorn's lemma. Yeah, if you are this kind of person, if you like puns, then you will enjoy it. If not, then probably if you are more into intellectual jokes, there's a well-known joke alluding to the equivalency of the Zorn's lemma, the well-ordering principle, and the axiom of choice, and it is attributed to Jerry Bonham. He said, "The axiom of choice is obviously true, the well-ordering principle is obviously false, and who can tell about Zorn's lemma," right? Perhaps suggesting na yung formulation ng Zorn's lemma, as you will see later, is much more complicated than the very naive and very simple-looking axiom of choice. And the well-ordering principle, nasabi ni Jerry Bono, when you think of it intuitively, mukhang false. Pero actually, apparently, it is true because it is equivalent to the axiom of choice. All right? Now, in pop culture, Soren's lemma was also mentioned in one episode of The Simpsons. You see here in the slide, parang merong hypnotist and he hypnotized somebody into proving Soren's lemma. And I don't have the power to hypnotize you guys, so we will skip the proof of Soren's lemma. But the proof of Soren's lemma can be written using the axiom of choice or together with other ZF axioms or the well-ordering principle. All right. Now, there's also a structural experimental film in the US that is entitled Zorn's Lemma, which starts with a series of photographs. It's non-narrative, and it is structured around the 24-letter Latin alphabet. Though I haven't seen it, nakita ko lang sa Wikipedia yung reference to this narrative movie. All right. Now, ano yung kahalagahan ng Zorn's lemma? Actually, Zorn's lemma is very much used in other parts of or in other fields of mathematics, not just in set theory. So maraming mga results in different areas na ang proof nila ay gumagamit ng Zorn's lemma. An example in functional analysis, the Han-Banach theorem, which is one of say the core concepts in functional analysis, is proven using Zorn's lemma. In linear algebra, it is used to prove that every vector space has a basis. Sa modern algebra naman, you can prove using Zorn's lemma that every commutative unital ring has a maximal ideal. Tapos sa topology, yung Tikhonov's theorem naman ay equivalent sa Zorn's lemma. And in first order logic, there's what we call the completeness theorem, which can be proven using some of the consequences of Zorn's lemma. So you will see, even though it looks like the conclusion of Zorn's lemma is very simple, it talks about maximal elements and when do they exist. All right. Now, napaka far-reaching ng applications niya. And probably it is because it might be partly due to the fact that it is equivalent to one of the cornerstones of set theory, which is the axiom of choice. Now, Zorn's lemma is also known as the Kuratowski or Kuratowski-Zorn's lemma, though medyo in popular readings, it is just called the Zorn's lemma. It was actually first proven by, or an equivalent version of it, was first proven by Kazimierz Kuratowski in 1922. Tapos later, there's another independent proof given by Max Zorn in 1935. Okay, now let's get going with Zorn's lemma. And as I've mentioned, medyo na-spoil ko kayo kanina, Zorn's lemma will talk about maximal elements. So let's first dig in and talk about what are maximal and similarly minimal elements are. So let's look at definition 1. It says here that if you have a partially or totally ordered set, an element Z is a maximal element if Z precedes X implies Z equals X. So kapag ka meron tayong nahanap na element nung set na nagdo-dominate kay Z, tapos i-imply nun na yung dominator na X ay equal kay Z, then we say that Z is maximal. In other words, the element Z is maximal if there is no element in A that dominates it, aside of course from itself. All right? So wala nang ibang element na mas lalaki pa or mas tataas pa kay Z doon sa poset diagram or sa lattice diagram. Or in other words, lahat ng related kay Z o lahat ng comparable kay Z ay mas maliit kaysa kay Z. All right? Now, on the other hand, an element W is said to be a minimal element of the poset A if and only if X precedes W implies W is equal to X. So that means kung meron tayong mahanap na isang element ni A na nagpre-precede kay W, ibig sabihin si W dapat ay equal kay X. Meaning there is no other element in A aside from W itself that precedes W. Kaya siya minimal, siya yung nasa ilalim ng poset diagram. Ibig sabihin, wala nang ibang element na comparable sa kanya na mauuna sa kanya. So in a poset diagram, the maximal element is a terminal element on the top. Ibig sabihin, wala nang line that can be drawn from the maximal element upward in the chain or in the diagram. Meanwhile, a minimal element is the tail end of a poset diagram. Ibig sabihin, wala nang line na magkokonekta dun sa minimal element pababa sa kahit ano pang element dun sa lattice diagram. Alright? So kaya ang tawag sa kanila maximal. Wala nang mas tataas pa na comparable sa maximal element. Wala nang mas bababa pa sa minimal element dun sa poset diagram. Alright? So those are the technical definitions na magiging go-to tool nyo when you try to prove statements about maximality or minimality of elements of a poset. All right. Pero let's look at a tangible example for you to more appreciate the definition. Let's look at example 2. Now we have a set A here consisting of the little letters A, B, C, D, and E ordered according to the lattice diagram shown below. The challenge is let's identify what are the maximal and minimal elements if they exist, right? So you can pause the video, write down your answers on a sheet of paper, think about it for a couple seconds, and then hit play because I will momentarily reveal my answers, okay? All right, so hopefully you have written down your answers. So I'm ready now to reveal the answers. Unahin natin, ano yung mga maximal elements? Actually, there is a maximal element here. Actually, there are two. Sino-sino sila? Si A at saka si B. Parehas silang maximal elements kasi wala nang line na nadodraw mula sa kanila pataas dun sa lattice diagram. Ibig sabihin, wala nang ibang elements aside possibly from themselves that dominates A. So si A dominates E, A dominates D by transitivity, A dominates C by transitivity, but no other element dominates A. Si A na yung pinakamataas among all of the elements that are comparable to it. In the same manner, B dominates all other elements comparable to it. Si B ay mas maliit kay B dominates E, B dominates C by transitivity, B dominates D by transitivity, but no element dominates B. Alright? So, ibig sabihin, si A at saka si B ay mga maximal elements. But neither of them are greatest elements. Kasi ang usapan natin, kung babalikan niyo yung previous recording, we said that an element is the greatest element if it dominates everything in the set. Right? Obviously, A doesn't dominate B. So si A, hindi siya pwedeng maging greatest element. Si B, hindi niya rin dinodominate si A, but it dominates all others, namely C, D, and E, but not A. So B cannot be the greatest element. But nevertheless, B is a maximal element kasi wala nang mas tataas pa sa kanya. So I hope now you can draw the line between between maximality and being the greatest element of a poset. All right. On the other hand, C and D are both minimal elements of the relation because there is no line drawn connecting C or D downwards to elements of the set. Wala nang nagpre-precede kay C at saka kay D. All right. Now, in contrast, C nor D are least elements kasi hindi niya piniperceive lahat ng elements kasi si C hindi niya piniperceive si D nor si D hindi rin niya piniperceive si C. So ibig sabihin hindi sila pwedeng maging least elements pero sila ay minimal elements. All right? And that gives us one nice discovery, an elementary fact about minimal and maximal elements. Now, minimal and maximal elements need not be unique, all right? There could be more than one maximal element or more than two maximal elements in a poset, in contrast to having only a unique least or a unique greatest element should they exist in a poset, right? Now, another example is the set, the open interval 0, 1, the set V here called V. These are the set of all real numbers that are strictly between 0 and 1 with the natural order. So that's the less than or equal to order. Then this has no maximal nor minimal elements. Now, the argument is the same as the argument that I made when I said that walang first and greatest element yung open interval 0 to 1. Kasi sa pagitan ng dalawang real number, laging meron pang isang real number. All right? So the same argument goes here. Kasi nga, wala tayong mahanap na element nung open interval 0, 1 na nasa dulo na nung lattice diagram. Again, if you want to recall, so the lattice diagram for the open interval 0, 1 looks like this. 0, 1, natural order. Lahat ng nasa kaliwa, piniproceed nila yung nasa kanan. So if you'll be looking for for minimal elements, titingnan mo ano yung element na nandun sa kaliwa at wala nang nasa kaliwa niya. All right? Halimbawa, ito yung candidate ko. Halimbawa, tawagin ko itong halimbawa, ito si 1 over 100. If it is the minimal element, then there should be no other element of the open interval that is to the left of 1 over 100. But again, by the density of the set of real numbers, between 0 and 1 over 100, we can find another real number, say 1 over 200. All right? Tapos, si 1 over 200, it precedes 1 over 100, therefore making 1 over 100 not a minimal element. And then you can continue the argument and say na, oh, between 0 and 1 over 200, there's another real number, so 1 over 200 cannot be a minimal element. All right? So wala siyang minimal element. Now, I want you to think about it and tell me probably when we next meet, or you can drop down a comment in the video. Do you agree na kapag yung poset mo ay totally ordered, if you have a total ordered set, do you agree that the first and the last element or the first and greatest element coincides with the minimal and maximal elements respectively? So let me know, comment down below, guys. All right, so pag-isipan niyo. Okay, let's take a look at exercise 4. And I think this is the divides relation, which we look at illustration 4.1.10. All right. So we have the set containing 1, 2, 4, 6, 8, 10, and 12. And the partial ordering is divides. So we say that x precedes y if and only if x divides y, or y can be written as an integer multiple of x. All right. So nakita na natin itong poset diagram na to before. And let's try. Can you identify the minimal and maximal elements if there are any? So you can pause the video now, think about your answers, write it on a piece of paper, and then come back momentarily as I will reveal my answers to exercise 4. All right, so hopefully you have written down your answers to this problem. Let's try to see what are the minimal and maximal elements. So kulayan ko ng yellow yung mga sa tingin ko ay minimal elements. So ang usapan, pwede mong tingnan yung poset diagram. Pag wala ka nang nakita na elements sa ilalim niya, all right? When I say ilalim, dapat connected by a line, then it would be a minimal element. Now, it would be a maximal element if there is no line drawn upward toward the diagram from that element. So that being said, I can say that 1 is a minimal element. And take note of the article that I'm using. I'm using a minimal element because, again, the minimal and maximal elements need not be unique. And for here, I think there are at least 2 minimal elements, right? So 1 is a minimal element because 1 precedes everything and nothing precede 1. Right? Walang ibang element ang nasa ilalim na ni 1 sa poset diagram. All right? Now, another minimal element is the number hindi pala si 10. Actually, isa lang pala. Sorry, akala ko dalawa siya. Isa lang yung minimal element, and that is the number 1. And then what are the maximal elements? Let's color them, say, green. All right? Ano yung mga maximal elements? Wala dapat elements na nagdo-dominate sa kanila along the chain. All right? So si 12 ay isang maximal element because there are no other elements aside from itself that dominates 12. Though si 12, hindi siya greatest element dun sa ating poset kasi hindi niya dinodominate lahat. Alright? Magkaiba yung tinitingnan natin. Ha? Sa maximal element, wala dapat nagdo-dominate sa kanya. So si 12, walang nagdo-dominate sa kanya kasi wala nang line drawn from 12 upward into the diagram. So 12 is a maximal element. But 12 is not the last or the greatest element. Bakit? Kasi hindi niya dinodominate lahat. Para maging last or greatest element, dapat i-dominate mo lahat ng laman ni set A. Note that 12 doesn't dominate 8. There is no line joining them, nor a top to bottom line joining 12 to 8. So, ibig sabihin, hindi magiging last or greatest element si 12 kasi hindi niya na-dominate lahat. Pero dahil walang nagdo-dominate kay 12, ibig sabihin, isa siyang maximal element. Alright? Another maximal element here is 8 kasi wala nang nagdo-dominate kay 8. And then 10 is also a maximal element kasi wala nang nagdo-dominate kay 10. Then 4 is neither a maximal nor a minimal element because there is an element that precedes 2. Hindi siya minimal, that precedes 4. Hindi minimal si 4 kasi piniprecede siya ni 2. So merong nasa ilalim niya. Tapos si 4, hindi rin siya maximal kasi may nagdo-dominate sa kanya. Alright? Si 4 is dominated by 8. So 4 cannot serve as a maximal element. So in this exercise, we only found one minimal element, and that is 1. And then we have 3 maximal elements, namely 8, 10, and 12. All right? So I hope you guys agree with my answers. And hopefully, you now have a good grasp of what a maximal and minimal element is. All right. Now, to aid our understanding, some nice, interesting facts about maximal and minimal elements are enumerated in remark number 5. The first one is that if X is the first element of A, then X is the unique minimal element in A. The last element in A is also the unique maximal element in A. So, ibig sabihin, kapag meron tayong first element, siya automatically yung kaisa-isang minimal element. At napatunayan natin yan sa example na to. Note that 1 was dominated by everything in the set. Pinrecede ni 1 lahat nung nandoon sa set A natin. So, ibig sabihin si 1, siya yung first element nung relation. Alright? O nung poset na to. Kasi 1 precedes everything. Na unahan niya lahat ng elements ng set A. At dahil siya yung first element, it is but easy to realize na, nga no, Kung siya yung first element, then siya lamang yung kaisa-isang magiging minimal element. Kasi piniproceed niya na nga lahat eh. So dinidisqualify niya na yung ibang elements ni A from becoming a minimal element kasi lahat ay na-proceed niya. Alright? And the same thing goes true for the greatest element if it exists. Kapag ka meron kang greatest element, siya lamang yung kaisa-isang maximal element. Pero pag wala tayong pag wala tayong greatest element, then there could be more than one maximal element. All right? So bullet number 2, if A is totally ordered, it can contain at most one minimal element, which could be then the first element. Likewise, if it can contain at most one maximal element, which would then be the last element. All right? And third bullet, every finite partially ordered set has at least one maximal element and at least one minimal element. All right? Siguro yung bullet number 3, mas obvious siya pag tinignan natin yung poset diagram. Kasi kung finite lang yung poset diagram, ibig sabihin laging matitrace natin ano yung pinaka nasa dulo. At yung nasa pinakadulo sa ibaba, yung wala na tayong pupuntahan pababa mula sa kanya, then siya na ay isang minimal element. Tapos yung isang element na nandun na sa taas, wala na tayong aakyatan mula sa kanya, siya na ay isang maximal element. The problem would be the case will be different from for infinite partially ordered sets na medyo iba yung usapan kapag ka infinite na yung set. Pero pag finite, kaya nating ilista yung poset diagram in a nice and terminal way. Okay? Now, moving on, aside from concepts of maximal and minimal elements, we also need to talk about upper bounds, least upper bounds, lower bounds, and greatest lower bounds, right? Let's start off with with definition 6. We start again with a poset, all right, A and the precedes relation, and then we'll consider a subset B of the set A. And we say that an element Y in A, so dapat yung Y natin ay manggagaling kay capital A. That element Y will serve as an upper bound for B, if and only if that element Y will precede all X element of capital B. Kapag si Y ay magiging upper bound kapag ka mas mataas siya in the poset diagram kesa sa lahat ng elements ni X. Kaya siya upper bound. Dinodominate niya lahat ng elements ni subset B. And if the element Z is the smallest among the upper bounds, then it is called the least upper bound. Medyo obvious yun, no? Kolektahin nyo lahat ng upper bound. Tapos tingnan nyo, ano yung first element? Ano yung least element ng set of all upper bounds for the set B? That least element, if it exists, is what we will call the least upper bound, or better yet, call it the supremum for B. Right? So again, Z will be the supremum if and only if Z is an upper bound and it will precede all upper bounds Y of the set B. All right? Our notation for the supremum is sup of B or LUB of B. Parehas lang sila. Mas madali lang sabihin yung supremum kaysa least upper bound, pero mas madaling tandaan yung least upper bound kasi nga upper bound siya tapos siya yung pinakamaliit na upper bound. All right, similarly, we can talk about lower bound and the greatest lower bound, all right? And that's in definition 7. Again, we consider a set A together with a partial order on it and a subset B of A. Then an element T in A, again, magiging lower bound lang siya kapag ka-element siya nung poset capital A, tapos siya dinodominate siya ng lahat ng elements ng set B. All right? It will be a lower bound if it will go before, or in other words, if it will precede all element of capital B. Kaya siya lower bound. Mas maliit siya in terms of the partial order kesa sa lahat ng element ni B. Now, if you will collect all the lower bounds for a set B and get the greatest element or the last element of the set of all lower bounds, what we will get is what we call the greatest lower bound. Medyo obvious siya from the terminology, or kung gusto nyong mag-sound nerdy, you can call it the infimum. All right? So the infimum for B, written as inf B or GLB of B, is the greatest lower bound of B. So W would be the infimum if it is a lower bound and it dominates all lower bound or all lower bounds for the set B. Okay? So again, tignan natin paano nag-ooperate itong mga definitions na to by looking at specific examples. Now, let's consider this poset. All right. So meron tayong set V containing letters from A to G. Tapos ang order ay represented by this poset diagram. And then let's consider the set B. Yung set B na subset ni V ay D, E, C. Incidentally, first three letters of the month December. All right. Now, kolektahin daw natin. Hanapin natin lahat ng mga upper bounds. Oops, sorry. Hanapin natin yung mga upper bounds for the set B. Upper bounds, so lahat ng mas mataas sa mga elements ni B. Everything that dominates elements or that dominates all of the elements of the set B. Note that A dominates C, dominates D, and dominates E. So that makes A an upper bound. Sorry, hindi ko pala kayo na-warningan na nabigyan ng time para ibigay yung mga upper bounds at lower bounds. Try it first on your own. So you can do that now. I gave you an example. One of the upper bounds is A. So you can pause the video now to get the other upper bounds and the lower bounds if they exist. And then momentarily, I will show my solution. All right. All right, so I'm back. Hopefully you have written your guess for the upper bounds and the lower bounds. So let's continue. Aside from A, I dare say that B is also an upper bound. Bakit siya naging upper bound? Kasi B dominates C, B dominates D, and B dominates E. Doon lang ako sa tatlong elements ni B nagbabase kasi ang hinahanap ko lang ay upper bounds ni set B. So with that, B dominates D, C, and E. So B is an upper bound. All right? And then there's another one. Hopefully you didn't miss this one. C is also an upper bound for B. Bakit? Because C dominates itself by reflexivity. All right? And then C dominates D. And then C dominates E. Therefore, C is also an upper bound for B. All right? And then alam na natin yung mga upper bounds. Ang upper bounds natin ay si A, si B, at saka si C. Can we compute the supremum of the set B? The supremum of the set B is the least upper bound. What is the smallest upper bound? So tingnan natin, kunin natin yung first element ng set containing A, B, and C. Now, basing it on the poset diagram, we see that C precedes A and C precedes B. So ibig sabihin, considering the set containing A, B, C, C is the first element. So we can say that the supremum of B is the set containing C. Kasi pini-precede ni C lahat ng upper bounds ni B. All right? Now let's look for the lower bounds. Ito naman, yung mga lower bounds, dinodominate sila ng lahat ng elements ng set B. Right? Kasi nga lower bound sila, mas mababa sila dapat dun sa poset diagram. Now let's look at F. Let's check if it is a lower bound. Well, C dominates F, D dominates F, and E dominates F. So that makes F a lower bound. And then G dominates, or G precedes E, G precedes C, but G doesn't precede D. There is no route going down from D papunta kay G. So hindi dinodominate ni D si G. So that makes G not a lower bound. because G doesn't precede all elements of the set V. So isa lamang yung lower bound natin, and the lower bound is F. At dahil isa lang yung lower bound, kukunin ko yung infimum o yung greatest lower bound. So by default, siya lamang ay si F. Okay? And that's the notes. All right? So let's try to see if I have another example here. All right, let's see this one. Let's go back to the inclusion relation on the set containing little a, little b, and little c. Tapos kunin ko si curly C to be the set of all singletons and the power set of A. Again, pag sinabi kong singletons, ito lamang yung set na isa lang yung laman. Set A, set containing B, set containing C. Hanapin natin lahat ng upper bounds, lahat ng lower bounds para sa kanila, and let's determine if the supremum and infimum of curly C exists. All right? Now, let's see. Ano yung mga upper bounds? So you can pause now and answer it on your own first, and then momentarily I will reveal my answers. Okay, go for it, guys. All right, so I'm back. Hopefully nagsulat kayo, nagtry kayo. Let's see the upper bounds. So ang upper bounds ay dapat lahat ng nagdo-dominate sa lahat ng elements ni curly C. So sila dapat ay nagdo-dominate sa lahat ng elements ng curly C. Now, our candidates, of course, are those that belong to the upper echelon of the lattice diagram. Mas mataas dapat dun sa set containing A, set containing B, and set containing C. Sila yung mga candidates natin. Of course, we can say that the set A itself dominates A, or dominates the set containing A. It dominates the set containing B, and it dominates the set containing C. So I can list A as an upper bound. Okay? Let's check the set containing AC. The set containing AC dominates the set containing A. It dominates the set containing C, but it is not comparable to the set containing B. Therefore, the set containing AC does not dominate the set containing B, disqualifying it from being an upper bound. Kasi ang usapan, magiging upper bound lamang siya kapag ka dinodominate niya lahat ng elements ni curly C. The same thing goes for the set containing AB. It dominates both set containing A and set containing B, but it is not comparable and therefore doesn't dominate the set containing C. AB is likewise not an upper bound. And then sa set containing BC, hindi rin siya upper bound. So in this case, we only have a single upper bound, and then that's the set containing, or that is just the set capital A, right? Para makuha yung supremum, remember, the supremum is the least upper bound. Kunin natin yung first element ng set containing all the upper bounds, pero nag-iisa yung laman niya. So ibig sabihin, ang supremum ay equal lamang kay capital A. All right? And then lower bound. Tingnan natin ang lower bound para kay set curly C. Titingnan natin ngayon, ano yung mga elements ng power set ni A na nandun sa ilalim ng mga singletons. Nag-iisa lamang siya, the empty set. And note that the empty set precedes set containing A, precedes the set containing B, and precedes the set containing C. Therefore, it qualifies as a lower bound. And not just that, it is the only lower bound, making it also the infimum of curly C. All right? So if you want to get more practice with this, you can just arbitrarily choose what would be your curly C. Pwedeng gawin nyo, halimbawa, gusto kong i-check kung ano yung mga upper bounds, lower bounds, kung meron bang supremum or infimum. Halimbawa, itong set curly C na to. Yan yung gamitin kong set curly C. All right? So in my example so far, I think we always find a supremum, or we always found a supremum and an infimum. But in general, suprema and infima need not exist. All right? Siguro nakita nyo na to in your gen math or your elementary algebra. Meron na kayong tinignan doon ng mga supremum, infimum, lower bound, or upper bounds for the set of real numbers. And you might have learned there na may mga subsets si R together with the natural order na walang suprema at wala ring mga infima. All right? So yun yung kaso dito. Though we are dealing here with finite sets and they happen to be well structured, kaya nagkaroon ako lagi ng supremum at saka infimum. Pero that is not necessarily the case in general. All right? Ito pala, may binigay siya. Halimbawa, example 9. So we look at the set of rational numbers Q together with the natural order. And we consider the set B, all right, which is the set of all rational numbers x such that x squared is strictly between 2 and 3, all right? So there would be infinitely many upper and lower bounds. For instance, 5 is an upper bound for the set B because 5 squared is 25. So it is outside of the set B, all right? And it is larger than any element of the set B. Kasi kung titingnan nyo tong set na to, siguro ang laman niya lang ay mga rational numbers that are in the interval square root of 2 until square root of 3. And 5 obviously is outside this interval. And in fact, 5 is larger than all numbers that are smaller than square root of 3. All right. So because 5 is an upper bound, 6 is an upper bound, 7 is an upper bound, square root of 3.5 is not an upper bound because it is not a rational number. All right. Remember, ang upper bounds dapat nagbibelong dun sa superset. Ang superset natin sa poset na to ay si Q. So mga rational numbers that are greater than square root of 3 ang ating mga upper bounds. Okay. In the same manner, we have infinitely many lower bounds, pero wala tayong supremum at saka infimum. Alright? Bakit wala tayong supremum or infimum? Kasi nga ang mga, halimbawa, lower bounds. Ang mga lower bounds ni square root of 2 ay mga rational numbers na mas maliit kay square root of 2. So ano ba ang square root of 2? Ang square root of 2 ay 1 point something. So si 1 ay isang rational number na mas maliit kay square root of 2. So 1 is a lower bound for the set B. However, there's a theorem, or actually it is not hard to imagine, that between two real numbers, there's always a rational number. That's what we call the density property of the rationals in the rationals in R. Sa pagitan ng kahit anong dalawang real numbers, merong at least isang rational number. So, ibig sabihin, sa pagitan ni 1 at saka ni root 2, meron pa diyang isang rational number na nagtatago. Tawagin nating x1. Okay? So, siguro 1 plus 1 over 10. 1 over 10 is one example. All right? So, tama nga ba? Yeah, I think so. Pero sure ako, meron pang isang rational number. Tinawag ko siyang x1 sa pagitan ni 1 at saka ni root 2. The very existence of x1 denies 1 from being the infimum. Kasi para maging infimum siya, dapat yung greatest lower bound. Lower bound nga si 1, pero the density property of Q in R guarantees that there exists another rational number x1 between 1 and root 2. So x1 on itself is a lower bound for the set B that is greater than 1. So 1 cannot be the greatest lower bound. Okay? Now, again, I will apply the same density property this time for x1 and root 2. They're both real numbers. Tapos the density property says, sa pagitan ng dalawang real numbers, merong natatagong at least isang rational. And let's call that rational number x2. x2 will be a lower bound for B, kasi mas maliit siya sa root 2. Pero the existence of x2 will prevent x1 from being the greatest lower bound because x1 is less than x2. All right? And then you can imagine this process being done over and over again until we will hit a dead end. Parang infinite loop lang itong daraanan natin na wala tayong makukuhang um, greatest lower bound. Because pag meron kang candidate, lagi ka pang may mahanap na lower bound na mas malaki kesa dun sa candidate mo na yon. Alright? This would have been a different story if our poset is the set of real numbers. So makakasama na si square root of 2, and actually square root of 2 will be the infimum, all right, for the set B if you're talking about the set of rational numbers as our poset. Ang naging dahilan lang kung bakit hindi naging infimum si square root of 2 kasi hindi siya rational number, tas ang poset lang natin ay set of rational numbers. Okay? All right? So, okay, so I think that's it. And we're ready for the statement of Zorn's lemma. All right. I don't know if I mentioned already what is the difference between theorem, lemmas, corollaries, and so on. Theorems, ito yung usual propositions that we have proven to be true. All right. Yung lemma at saka corollary, sila ay mga theorems din sila, mga propositions sila. Pinoprove natin sila, they are statements. However, one theorem is called a lemma kapag ka yung significance niya ay pang-prove siya ng mga mas mahalagang results. So in that case, you can think of a lemma as a proposition whose significance or whose essence is not on its own right. So hindi yung sarili niya, yung significance niya. Ang significance niya ay yung mga results na pinuprove gamit siya. So Zorn's lemma is one example of a theorem or a proposition that whose significance lies on what is to follow, on what are the results that are proven using this proposition. Sabi ko nga kanina, ang daming mga results in all areas of mathematics that are proven using Zorn's lemma. That's why probably people called it a lemma rather than Zorn's theorem. All right? Now, anong sabi ni Zorn's lemma? So Zorn's lemma says, let's consider a non-empty poset A in which every totally ordered subset has an upper bound. Okay? So meron tayong poset capital A. Tapos, titingnan natin lahat ng kanyang mga subsets, mga totally ordered subsets. Right? Kapag ka lahat ng totally ordered subsets niya ay may upper bound, then A contains at least one maximal element. Right? And probably here, the intellectual joke later ni Jerry Bona na sabi niya ay, the axiom of choice is obviously true. Makikita niyo yan later in the next video. The well-ordering principle is obviously false. Nakita natin yan from last time. And who can tell about Soren's lemma? Probably because of the complexity of the statement of Soren's lemma. But again, that is just a joke due to Bona. We know that Soren's lemma, the well-ordering principle, are both true because they are equivalent to the axiom of choice. All right? So sabi ni Soren's lemma, sa isang poset kung saan lahat ng totally ordered subsets ay may upper bound, then si A ay may at least isang maximal element. All right? Now, we do not have the necessary background to look at the consequences of Zorn's lemma. Kanina enumerate ko yung mga theorems, usually yung mga sikat na theorems na napuprove using Zorn's lemma sa functional analysis, sa linear algebra, sa modern algebra, sa topology, at saka sa formal logic. Pero we don't have the necessary background to tackle them yet. So they will be discussed in your future major courses, but at least now I have given to you the statement of Zorn's lemma. All right. Now, there's a weakness to Zorn's lemma as similar to the weakness of the well-ordering principle. Zorn's lemma is an existence result. It tells us now when all the premises are satisfied, then the set capital A will contain at least one maximal element. It doesn't say exactly how many maximal elements the set A has. Sabi niya lang may at least isa at wala rin siyang sinabi kung paano natin siya i-construct. But again, in math, usually existence is enough. Proving the existence of something is a big thing already. So it's just for us to see how to construct such maximal element. All right. And I think I can stop the video here about Zorn's lemma. Let me just see if I have forgotten something. Oh, there's a quote, a nice quote, and maybe I'll end with this. A quote due to, let me see, to Sir William Timothy Gowers, who is an English mathematician who was awarded the Fields Medal, which is basically you can which is the one of the biggest prize in mathematics. Probably you can equate it to the Nobel Peace Prize for the Nobel Prize for mathematics. Sabi ni Sir William Timothy Gowers, if you are building a mathematical object in stages and you find that one, you have not finished even after infinitely many stages, and two, there seems to be nothing to stop you continuing to build, then Zorn's lemma may well be able to help you. All right. So pag nandun na tayo sa nagko-construct tayo ng mathematical objects stages by stages. So we are building one concept over the other. And hindi tayo natatapos kahit infinitely many na beses natin gawin yung process. Tapos hindi natin nakikita yung dulo ng tunnel o dulo ng process na ginagawa natin. Then sabi ni Sir Gowers, yeah, mukhang matutulungan ka ng Zorn's lemma. Because Zorn's lemma promises that your set or your stages will have at least one maximal element. At sabi nga, pag nandun ka na sa maximal element, you cannot go up anymore. So kailangan mo na mag-branch out sa kabilang connections dun sa lattice diagram. All right? So that's it for us, guys, for Zorn's lemma. I hope you enjoyed the lecture. So let's let's uh, let's see each other again on the next video where I will talk about the axiom of choice. All right? Bye, guys.